Okay, this is fine. So let's move forward. So far, as I said, we have already discussed together many issues. We discussed about the estimation of water resources availability. We discussed about one infrastructure in detail, which is river barrages. During our discussion, frequently we called into play statistics and probability. And we called into play statistics and probability, you may remember, for estimating low flows, and also for the river barrages, we said we need an estimate of the peak flow. And these estimates, we pointed out, very frequently are to be derived by using the theory of probability and statistics. First of all, what is statistics? Statistics is the science that makes inference from data. So you get data, you observe something, and you try to make inference to understand what you are observing works in order, in our case, to make design. This is statistics, inference from data. Inference from data can be done by using several theories. And I make some examples. Fuzzy theory, you may have heard about fuzzy theory, or possibility theory. Probably you didn't hear about possibility theory, but it's another alternative to fuzzy logic. And there is probability theory. So probability is a way of making a statistical inference. It's a theory that allows us to make inference from data. Making inference means try to understand something. And basically, what we want to know, let's be very technical. What do we want to know? In this case, I make explicit reference to the estimation of peak flow, which means we want to know something more about the frequency of floods and magnitude of floods. So we want to understand a physical process, which is a process that is governed by the law of physics, originating a flood event. And I say the law of physics because we are talking about a fluid that moves, and therefore we need to refer to the laws of physics, not chemistry, not ecology, not biology, it's physics. Because you know that physics, the purpose of physics is to study the movement of bodies. And in our case, the fluid is a body of water that moves, and therefore we have to refer to the laws of physics. It's a completely physically based process. The problem is that we don't know how to describe it in mathematical terms. We have some ideas, but these ideas, when we try to describe the process, the phenomena in mathematical terms, it turns out that our description is not perfect. It's not like describing the movement of a body in a void space. We know that Galileo made experiments from the Pisa Tower in order to study the time required to bodies to reach the ground. And he was able to derive a physical relationship to describe this movement of bodies in an almost perfect way. The only uncertainty is given by friction with air. But we know today that if we are in a void space, we can describe this physical process in mathematical terms with no uncertainty, meaning that the description is perfect. If we try a similar description with floods, we cannot get to target. We cannot describe floods perfectly. There is uncertainty. And therefore, when there is uncertainty, you need to make inference from data. So you try to understand a process, a phenomenon. You cannot describe it precisely, exactly, and therefore, what does the scientist do? The scientist makes experiments, takes data, and tries to describe the phenomenon by using the observations. And observations can help us to improve the theory. And therefore, by improving the theory, one could eliminate uncertainty. Otherwise, at least observations allow us to describe uncertainty. And that's it, meaning that once that we have a description that is uncertain, and we can provide an estimate of uncertainty, I mean, this is, for the design purposes, is nevertheless fine. So we have to make inference from data. This is also what Galileo did, but in his case, he was able to provide, to improve the theory and to provide a correct mathematical representation. For the case of hydrology, we still didn't succeed. Through observation, we are trying to improve the theory, but still there is uncertainty. And in my opinion, uncertainty will never be eliminated in hydrology because there is uncertainty in the observation themselves, and also we cannot describe the control volume precisely. So even if we completely understood what happens when it rains, even if we completely understood that when it rains and after the rain, even if we completely understood that, probably we will never be able to specify the geometry of the control volume, we will never be able to specify precisely initial and boundary conditions to integrate our differential equation, and therefore most probably uncertainty will always be present. And therefore we have to call into play a theory to explain uncertainty. And therefore we call into play statistics in its numerous branches. In my opinion, the most efficient way to deal with uncertainty is the theory of probability. In any case, it is the most frequently used for technical purposes. So we need to learn something about probability. But on the other hand, probability may be a very complicated science, a very complicated theory. So we need to be very technical, very fit for purpose, because I don't want to make a whole subject 48 hours of teaching on probability. I want to dedicate to probability a couple of hours, 3 hours, but still, I think it is important that we understand the essence. What is probability? What is statistics? Statistics, I already defined it. What is probability? And why do we use analytical relationship called probability distributions to explain what related to floods? Okay, so the purpose of this lecture, which I'm introducing now, is to provide the basis, the very few bases, only those that are necessary to us to fully understand, nevertheless, what is probability and why we use it. I will make reference to flood flows, but at the same time, you may make reference to low flows. It doesn't make any difference. I mean, probability is probability, and you can treat any kind of variable by using the theory of probability. I'm now referring to flood flows because it is important for us to estimate, to design river barrages, for instance. And also in any water resources system, when you deal with the rivers and you take water from rivers, it is important to estimate the flood flows, always. Okay, we already know what is an hydrograph, and in particular, an hydrograph is a graph of river flows along time. We are now interested in the peaks of the hydrograph, which are the flood flows. And first of all, let's keep in mind what are the basic independent variables for estimating the flood flows. The flood flows refer to a return period, which I will define. They refer to a river cross-section. So when we talk about a flood flow, we always have to specify where. And in turn, the river cross-section refers to a catchment. So we always have to say the flood flow of the Po River at Ponte Lagoscuro, at Poretto, at Piacenza. Always the location must be specified. And the location means the location of the considered river cross section, or cross river section, sorry. Okay. And again, I will define what is the retro period later. But let me anticipate that the return period basically defines how much a peak flow is extreme. Because the term peak flow by itself doesn't mean anything. Peak of what? Annual, peak flow of the year, peak flow of the month, peak flow of the last 100 years. So we always have to estimate the frequency at which we have to specify the frequency to which the flood flow refers. Let's suppose that you have an hydrograph, an observation of an hydrograph like for the Po River, which is 90 years long. You may refer to the peak flow, to the yearly peak flow, the peak flow in each year, or you may refer to the peak flow again in a month, a peak flow in a week, a peak flow during the whole 90 years, which is the top. So you see that always we need to specify a time step to which we refer. And this time step implicitly refers to the frequency with which a peak flow occurs. It is understandable by intuition that if you take a relatively low level of peak flow, this will happen more frequently. If you take the top flow during the 90 years history of the Po River that we have available, of course the top has occurred once in 90 years. We are not expecting that this top, which is very high, occurs frequently. So you understand that the peak flow depends on its frequency. Okay. And we will specify the frequency by defining a return period, which is extremely important. And keep in mind that we are talking about peak flow, which is an extreme. The same reasoning can be done for the opposite extreme, the drought flow. So for the Po River, you can get the minimum along the 90 years, and the minimum is an extreme, which has a very low frequency. Okay? And let's define the return period later. This is an example of river cross-section. Then there is the definition of what is a contributing catchment, and we already defined it. And then let's talk about models for estimating the peak flow. Again, there are several models for estimating the peak flow, and some of them are not probabilistic. Some of them indeed try to write physical models for estimating the peak flows. But still there is uncertainty. So if one wants, as I said again, to describe this uncertainty, then it's better to refer to probability theory. And what is the idea underlying probability theory? The idea is that we consider these events, these flood events, as random events. Events that happen by chance. And why by chance? Because we cannot, with our physical knowledge and physical basis, estimate precisely when these events happen. And therefore we are needed to assume that they happen by chance. And let me provide us a very simple example. If you toss a coin, you have two alternatives in order to try to predict what will be the outcome. You can describe the movement of the coin with the laws of physics, because it's nothing else that a body that travels into the air while rotating and then gets over the floor and then falls over a face. It's a body that moves. So in principle, the laws of physics allow us to understand what the outcome will be. It's for sure possible. On the other hand, it is extremely complicated because one needs to know what is the force that my finger gives to the coin and what is the momentum. So there is a rotation that we give to the coin and there is a force that we give to the coin, and we need to be able to measure precisely what is the pulse that my fingers give to the coin, and this is almost impossible. Even if we were able to estimate with precision what is the pulse that is given to the coin, then we have to predict the movement of the coin into the air, and then we have to predict its position when it lands over the floor. And given that the coin has a geometry that is very complicated to describe, even a very small difference in the position of the coin when it lands over the floor causes a different outcome. Because think of the coin that falls over the floor by standing on its side, and then to determine on which, standing on its edge, then to determine on which side the coin falls, it's extremely complicated, because if you make even a small mistake in determining the position of the coin, the outcome is different. And therefore it turns out that it's impossible for now, today, to describe and to predict deterministically, precisely, what is the outcome from tossing a coin, and probably it will never be possible. And therefore, what can we do? First, we can reason in terms of probabilities. Not first, we can reason in terms of probabilities, which is, I think, a viable solution, because if I cannot predict deterministically, I have two ways to follow, two possible ways to follow. So either I can look at the coin and say, without making any experiment, I can say, if I toss this coin, I have only two outcomes, which are head or tail, and these are, I look at the coin and I say, these are equally probable. So basically I have 0.5 probability of getting a head and 0.5 probability of getting a tail, and this is already a good prediction. I mean, I don't have a way of making a correct prediction without uncertainty. I have some uncertainty in it, but it's already very useful. Another way, because you know, when you look at the coin, you couldn't see, you may miss that the coin is not fair, it's loaded. Loaded means that there is a higher probability that it falls on a side rather than the other side. It means that it's a load coin. You may miss it. And therefore, another way is to make an experiment. Like you toss the coin 100 times and then you realize that you have a probability of 0.5 of getting a tail. And this is a way to determine the probability through an experiment. At the end of the story, whatever is the way that you followed, you get a prediction which is uncertain but still useful. Still useful, I mean, because think in terms of river flows. If you get a prediction that says that your river flow is maybe between 10,000 and 12,000 cubic meters per second, it's still very useful. Okay, so what we do when we cannot write a deterministic model, deterministic means a mathematical model that precisely describes an outcome. What we do is to consider that these events occur by chance. And therefore we look at the data, or we make some reasoning in order to estimate the frequency with which they occur. This is what we do. And given that referring to random events, it's a bit not very handy, we prefer to associate events to numbers. So what we do in the case of peak flow, we associate to the flood the flow, the value of the flow. And we make an association between the event that we want to observe and the real numbers or integer numbers. For the case of head tails, we usually if we want to treat them in mathematical terms, we assign 1 to the head and 0 to the tail, or the other way around, which would be a binary variable, because there are only 2 outcomes. For the case of floods, we associate the peak flow to a real number. And this is the way that we use to observe phenomena. We associate numbers to them, which is very smart. And in this case, we implicitly define what is a random variable. It's an association between an event and the space of the real numbers, or integer numbers. So this is the random variable. So sometimes we speak about random variables, and we may wonder, what is that? It's very simple. It's an association between something that we observe and a number, which may be integer or real. Okay, and now for these random variables, we need to define what is probability. Remember that our need is to study the frequency. Our need is precisely like that. We need to study the frequency of these events, and therefore the frequency of the numbers. Tossing a coin, we need to study the frequency of 1 or 2, head or tail, or 0 and 1, whatever. So this is our aim, to study frequencies. Okay. The lectures are very long, but there is most of it is descriptive. First of all, keep in mind that every time that you have a physical knowledge of the phenomenon, even if this physical knowledge doesn't allow you, it's not sufficient to obtain a perfect description, nevertheless you have to use it. So there is a long discussion in my lectures about how to incorporate in probabilistic models our physical knowledge. It is very descriptive, and I leave this part to you to read, and I will make some examples later. So what we do in hydrology usually is to build a deterministic model and then estimate uncertainty by using a probabilistic model. And therefore, through the deterministic model, we take the physical knowledge into account. Okay. Here there is the definition of random variable. And so let's jump to the definition of probability. And probability is, there are some paragraphs here that are not needed. Probability, it's a way to measure the frequency of an event. So probability measures the frequency of an event. It's a very good idea, because what we need to estimate is the frequency. So let's measure the frequency through probability. And we choose to measure the probability through a number that is comprised between 0 and 1. So let's refer to an event, generic event, a flood, like a river flow for the Po River that is greater than 15,000 cubic meters per second. And the probability of getting this event is measured through a number that is from 0 to 1. 0 means that the event is impossible. So even in our current language, sometimes we say the probability is that tomorrow is, the temperature is 40 degrees is 0. Okay? 0 means that the event is impossible. Probability 1 means certainty. And sometimes we say that. We say like the probability of getting killed if you throw yourself from the 10th floor is 100%. 100% means 1. In relative terms, 100% means 1. So one is the event that is certain. So for instance, when we toss the coin, we usually say the probability of getting an head is 0.5, which means that the event is possible, but it's not certain. And then from 0 to 1, you have all the probabilities, and sometimes probabilities expressed in percentage terms. Like for the presidential election in France, we were told on Saturday that the probability of Macron to win was about 62%. At the end, he took about 65, I think, of the consensus, which you can already understand what it means. And you can also understand that is well associated to the frequency, because 65% is the frequencies of votes for Macron with respect to the total number of votes. So you can already see the association, probability to frequency. So now we need to define how to compute probability. First of all, when we define probability, there are several ways of defining probability. And today we agreed to refer to the axioms of Kolmogorov that basically say that the probability of an impossible event is 0. They say the axioms, probability is between 0 and 1. Probability of the impossible event is 0. And probability of the certain event is 1. And there is a fourth axiom that I don't explain now because I want to make the treatment simpler. So there are these axioms that basically say what are the basic requirements for measuring probability, but don't say how to compute it. We need to jump very quickly on the way to compute it. We want, as engineers, we want to compute probability, because probability then allows us to estimate the frequency of our extreme events. Okay, so there are two definitions of probability, and let me introduce them very quickly. There is a first definition which I want to anticipate, which is the Bayesian definition. The Bayesian definition is based on our degree of belief. You don't need, in principle, data. You may use data, but even if you don't have data, you may express probability as your degree of belief. Like, you look at the coin and you say the probability of getting an head, it's 0.5. Even without trying to toss it, you understand that the probability is about 0.5. And you can use this personal belief to define probability. The only thing that you have to take into account is that you have to meet Kolmogorov's axioms. So probability is between 0 and 1, or between 0 and 100%. And 0 means impossible, 1 means for sure. Plus one more, which I don't discuss now. So, for instance, on Saturday, when we were told Macron has a probability to win of 62%, this was a degree of belief, was not based on data. Or, indeed, they took some data, but the data were proxies, not direct data. They didn't try an election before, they just interviewed people. But we know that these interviews sometimes are reliable, sometimes not. So they didn't use data, meaning that it's impossible for an election to make an experiment. You cannot do an election now, 1 week before the real election, to make an experiment. You, at most, can make interviews, and then you elaborate your degree of belief. So these people said 62% is the probability to win, he won with 65. So the prediction was quite good, but was not perfect. So degree of belief is the first one. And look, degree of belief can be used by us. We look at a river, we look at the vegetation, we look at the past history, like what happened in the past year, did they experience floods, etc. And we come to an estimate of probability without looking at the data. And this is the Bayesian definition. And it is extremely important. I want that you get familiar with these terms, because sometimes when you don't know something, you tend to assume that what you don't know is extremely difficult. It's extremely difficult and complicated to use. Instead, this is not true for Bayesian. You see, it's very simple. It's probability based on your degree of belief. So I want to teach you these concepts because I tell you my experience, without knowing what Bayesian was in the past, I tend to assume this must be very complicated. So sometimes I want to introduce the term to let you know what are the concepts in order to make you familiar with them. And once that you are familiar, they become easy. Okay, now let's turn to the second definition, which is more, I think it's easier. It's based on experiments. So basically what you do is, with the coin, you toss it 100 times, and you count the number of times that you get an head. And then you say, perfect, so if I make n equal 100 attempts, and I get n equal 52 times head. Okay, then very simply I define the probability of getting an head as lowercase n divided by capital N, which means 52 divided 100, which is 0.52. And you see that in this case you see the clear analogy with frequency. In fact, this is called the frequentist definition. You equate probability to the frequency of an outcome, which is precisely what we want to do. We want to estimate the frequency of floods. And the frequentist definition allows us to fully understand that probability is very close to the frequency. And you may ask me, but what's the difference then? Why don't you call probability frequency? Because frequency means that you observed something, and you compute the frequency by looking at the outcome of your observations. Probability is something theoretical that you must be able to compute even in absence of observations. So I can't name it frequency, because frequency means that you observed something. I need to use another name, because I can estimate probability even by intuition. I cannot estimate frequency by intuition. So I need another name, but I can say that the two things are very similar. And if I have numbers, if I have data observation, I can estimate probability by using frequency. And of course you see that the estimate is not correct. The frequency is not equal to probability, because the probability of getting an head is 0.5. If the head is fair, the probability is 0.5. By experiment, I get an estimate that is very close, and I can assume that if I repeat the experiment many times, I get closer and closer to, with the frequency, to the probability. And look, people did experiments to prove that. Pearson was a famous statistician. He tossed the coin 24,000 times, and he got 12,024 heads, which is very close to 0.5. He wanted to prove to his colleagues 300 years ago, more or less, that when the number of attempts increases, he was getting closer and closer to the real probability. And this is what we will try to do here. We have observations of river flows, and we try to estimate. We look at their frequency, and we try to estimate probability, with special emphasis, in our case, on the peaks. But you see that in technical terms, it's very easy. Of course, then you get a book of basic probability theory, and you get a book like this, and it's very complicated. But if we look at what we need and the meaning, it's extremely simple. Okay, I propose to stop here, and then next Monday you must allow